So when we have a force acting on an object, so we've looked at 4 of them for sure, and we've added in a couple others with different monikers, okay? When a force acts on an object, it causes there to be movement. And when there's movement, there's displacement. When there is displacement, there is work being done. We briefly looked at this in grade 8 when we did the mechanical unit. Okay? So we get introduced to this new formula. Work is equal to force times displacement times an angle. And now displacement is not distance. What's the difference between distance and displacement? Direction? Yes. Distance is the total movement, whereas displacement looks at direction. So if you go north and then you go south, you would subtract those two. If you went north twice, you would add those two. Whereas distance, if you went north and then you went south, you would add those two vectors together to get the total that you walked, ran, swam, biked, crawled. Okay? The angle is the angle between the force and the displacement vector. So whichever way your force is going versus whichever way the object is moving. And we get introduced to a new unit. Not to us, is joules. Okay? Work is scalar, so we don't need a direction. And any type of force that we come across, force applied, force of friction, force normal, force of gravity, any force can do work. It's just a blanket force. Okay? Net work happens because of the net force acting on an object. And all we simply do is we modify the question to look like this. Okay? So in order for work to be done, the force in question needs to cause or hinder, right, an opposing force, the displacement of an object. We're going to look at 3 different situations. Let's look at these 3 situations here. If my force is moving in this direction and my direction of motion is in this direction, what can we say about those vectors? Are they going in the same direction? Are they opposing directions? They're what, Kyle? They're in the same direction. So when your vectors are parallel, okay, that means that theta is 0 degrees. Okay. Everybody grab their calculator. and enter in cos theta of 0. What answer do you get? Oops. 1. So then that means when we look at work, that force is equal, or work is equal to force times distance. Because anything multiplied by 1 is itself. Okay? That's okay. Okay. This is an example of one when the object is being moved in one direction and that direction happens to be the same direction of motion. Work is 1 because the force is causing displacement. Okay? So if you're moving in the same direction, your cos theta is 1. If I go back here and I'm applying a force this way, and my direction of motion is this way, which force do you think this is to begin with? Force of friction. It's working against, it's hindering. Okay? What's the angle between direction of motion and force? If this is 0, right? If this is 0, what would this one be? You're going from here and you're moving there. How many? 180, 180 degrees. Okay? So if I did the cos of 180 degrees, what value do I get? -1. My work is being done opposite of my force. Okay, it's working opposite of each other. So just like Avery pointed out that this is potentially the force of friction is an opposing force. It's hindering this object from moving. So it's negative work. Now, third scenario, we go back to the direction of motion being this way. But what happens if there's a force being applied this way? So the angle between the two vectors is what? Can I which? What's my angle between the two vectors? How much, Princess? 90 is 90 degrees. When I do the cos of 90, what do I get? 0. Which means what? If I have 0 angle, anything multiplied by 0 is, so there's no work being done. Okay, there's no work being done. Kyle? Yeah. Let's look at an example. Can I which? Can I move it which way? Cool exerts a force of 20 newtons to push a 5.5 kilogram crate 1.35 meters along a horizontal surface at a rate of 2.7 meters per second square. Determine the work Cool does on the crate and determine the work done by friction on the crate. So the first thing that we need to do is we need to draw a picture. So Cool exerts a force to push. So there's a force applied. 5.50 kilogram crate at a distance of 1.35 meters, and acceleration is equal to 2.7 meters per second squared. Okay, the first question asks the work Cool does on the crate. So when we look at this, the direction of motion is this way. The crate is moving this way. So my theta is going to be what? If the force and the direction of motion are the same direction, what is my angle? 0 degrees. So in order to find work, it's force times displacement times cos theta. So we can look at this one of two ways. We can just plug in the values, or we can recognize that the cos of 0 is 1. So we wouldn't have to put the cos theta in there. So the work done by Cool is going to be 20.0 newtons times 1.35 meters. Now, if you want, you can write in the cos of 0, but we know that the cos of 0 is 1. Okay? And we get what? How much work did Cool exert on that box? Give me in proper significant digits. 27.0 joules. Okay? Now it's asking you in the second one to calculate the work done by friction on the crate. So work done by friction is going to be equal to force of friction times displacement times the cos of theta. Let's draw ourselves a picture. This is the direction of motion, is this way. Friction is going to be working in which way? opposite. And so our angle is going to be our angle 180 degrees. So the cos of 180 degrees is what, Kyle? -1. Okay. Now, do I have force of friction? Nope. Force of friction is going to come from force net. Do I have force net? Not given to me. Can I calculate it? Yes. Because what's the base formula for force? Mass times acceleration, which is going to be 5.50 kilograms multiplied by 2.70 meters per second squared. Now I'm going to make a big leap here. I'm not going to do all of the fancy rearranging. I'm just going to write it out how it should be. Force of friction is going to be equal to 20 newtons minus 5.50 times 2.70. And so then my force of friction ends up being what? So the work due to friction is going to be 5.15 newtons multiplied by the 1.35 meters it moves, multiplied by the cos of 180 degrees, which we know to be -1. And so we get what for a value? What'd you get, Cameron? Oh. Remember that work is scalar. Okay? Okay. This says 1,385 kilogram car traveled at 61 kilometers per hour is brought to a stop while skidding 42 meters. What is the work done on the car by the frictional forces? There's a lot of information in here to process. Let's start with a picture. Okay, a box. Wrong one. Coal exerts. What happened to my question number 2? Did yours photocopy out of order as well? Oh, only I'm lucky to have that. Okay, the direction of motion is this way. Which way are the frictional forces going? Opposite. Those are the frictional forces. And pieces of information out of the question. My mass is 1,385 kilograms. My velocity is 61 kilometers per hour. I have a second velocity in there, right? Because it was brought to a stop. So VF is equal to 0 meters per second. And my distance was 42 meters. It's asking me to calculate my work due to frictional forces. So what's something I need to do before I move beyond this point right here? Convert. So I have kilometers and I want meters. There's 1,000 meters in 1 kilometer. I have hours and I want seconds. In 1 hour, there's 3,600 seconds. And so I get what for a velocity? Let's call it an initial velocity. Okay. All right. So straight up, in order to solve it, work due to frictional forces is equal to force of friction multiplied by displacement multiplied by cos theta. That's how we solve it. Do we have force of friction? No, this is what we're looking for. This we don't have. We have this and we have that. How do we solve force of friction? Force net is equal to what? This car was in motion. Is there a force applied? It was in motion. Is there force applied? No. Okay. So force net then is strictly equal to the force of friction. How do I solve for force net? Mass times acceleration. I have mass, it's 1385. How do I solve for acceleration? Given what I have VF, I have VI, and I have D. Which one? Look at your formula sheet. Which one? You're really close. Can we help Cedric and Kyle out? Is that what you were saying, Kyle? Close. Okay, if I want to solve for A, I'm going to have VF squared minus VI squared all divided by 2D. So 0 minus 16.94, keep all your digits, and you're going to square it. 2 multiplied by 42 meters. And I get what for acceleration? What'd you get, Rayleigh? Okay, I got negative 3.418. It's probably just due to decimals. Meters per second squared. Now that I have acceleration, I can find force net. Force net is equal to, pardon me, No, you're right. Mass times acceleration. What do I get for a value? Okay, so I get negative 4,733 and a bunch of decimals. Looking at this negative sign, what does that tell us? What can we already start to interpret? It equals negative work. Okay, now that I have force net, I can go back up and I can solve my force of friction. So force net being equal to negative 4,733 means my force of friction is going to be equal to negative 4,733. So work due to frictional forces is going to be negative 4,733 and change multiplied by 42 meters. And then one thing that we didn't look at was back up at the top at our picture, what's my angle? 180. And 108 cos of 180 degrees is equal to negative 1. Okay. So we're going to get okay. Let's just pause here for 2 seconds and let's go up and make a little bit of a modification. When we go back up here to force net is equal to force of friction, this comes from this formula. Force net is equal to force applied minus force of friction. Correct? Do we agree to that piece? We said that there was no force applied because it was already in motion. So force net is technically equal to negative force of friction. Okay? Do we all agree to this piece? Okay. I'm going to shift your mind a little bit. If I take this and bring it over here, and I say force net is equal to negative force of friction, and then I took my value, here's my negative, and I put what I calculated here. Hang on, I did that a little bit backwards. Okay. If I want to solve for force of friction, if I divide by negative 1, I remove the negative. So force of friction is equal to negative force net. Do we see the math in that? Okay. So then I went negative times negative 473.966 is going to be equal to my force of friction. So force of friction actually is going to end up being a positive value. If I did the true math, if I carry that down into here, this becomes a positive value, and then my whole answer becomes negative. And I did all of that side work to show you that a frictional force is an opposing force, which means that your work is going to be a negative value. And that negative simply indicates that the force being used is in the opposite direction of the direction of motion. So just like a negative sign telling us, if I look at Sig Dig's, just like a negative sign before told us left, down, away, backwards, south, a negative sign here tells us that the work is in the opposite direction of the force being applied. You don't have to put the negative in, but you need to understand what that negative represents. Yep. Okay? All right, a 50-kilogram box is pulled 11 meters along a level surface by a rope. If the rope makes a 35-degree angle with the surface and the force exerted through the rope is 90 newtons, how much work is done on the rope? Well, what does that look like? Here's our box. And it's being pulled along at a 35-degree angle. This is which force, this vector here? You got 4 to choose from. Force applied, force of friction, force normal, force gravity. Which one? Force applied. Okay. Is the angle between the force and the work being done? Yes, it is. Or not work, displacement, sorry. It is. So our knowns are it's a 50-kilogram box. The distance it's moving is 11.0 meters. Our angle is what? 35 degrees. And our force applied is what? 90. Okay? And it's asking us how much work is being done. So when I look, work is equal to force times distance times the cos of theta. My force is 90 newtons. My distance was 11 meters. And I'm looking at the cos of 35 degrees. So my work being done on the box is what? Okay? We don't need to go in depth and do the force applied in the X and the force applied in the Y and then figure all those pieces out, because the angle takes care of that in this particular formula. We're looking at the work.